Welcome to The Explainer. Today, we're diving into something absolutely mind-blowing. We are bridging the gap between the tiny, invisible world of subatomic physics and the massive, roaring reality of our industrial power grids. It's really the story of how humanity figured out how to unlock the very forces that hold the universe together and then actually channel them into the electricity that lights up our modern world. Let's get started.
To really grasp the gravity of what we're talking about, think about this striking Quranic verse from Surah At-Tarhim. It mentions a fire whose fuel is people and stones. Now, for centuries, the idea of using stones as fuel probably sounded like a total mystery, right? But honestly, looking at it today from our modern vantage point, it's incredibly profound. Because right now, humanity literally uses heavy stones, elements like uranium and thorium, to ignite these massive nuclear fires that power entire cities. But, before we can understand how giant machines harvest this energy, we really have to understand why the atom holds it in the first place.
So here's our roadmap for today. We're going to cover 1. The idea of nuclear plants. 2. The missing mass secret. 3. Fission and chain reactions. 4. Uranium enrichment. And finally, 5. How a reactor actually works.
Section 1. The idea of nuclear plants.
Historically speaking, we hit a huge turning point back in 1954. That's when the Soviet Union fired up the very first nuclear thermal power plant, pumping out about 5 megawatts of power. What's kind of fascinating, though, is how uneven the adoption has been since then. For instance, as of today, there actually aren't any operational nuclear plants in Arab countries.
Okay, let's dive into the sheer scale of this, because we are talking about energy density unlike anything else on Earth. If you convert just 1 single gram of mass into pure energy, you produce 25 million kilowatt hours. To put that into a perspective we can actually wrap our heads around, that 1 tiny gram produces the exact same energy as burning 5,000 tons of coal. It's just a staggering realization of the immense potential locked inside the atom. But if a single gram holds that much power, where is all this energy actually coming from?
That brings us to Section 2, the secret of the missing mass and Einstein's equation.
It all starts with this mind-bending physics anomaly. It's literally like a giant puzzle. On one side of the scale, if you weigh 2 protons and 2 neutrons completely individually, their combined mass is exactly 4.0320 atomic mass units. But when you take those exact same particles and bind them together to form a single helium nucleus, the total weight suddenly drops to 4.0015. The whole is literally lighter than its separated parts. You've got this tiny difference of 0.0305 atomic mass units. So where on Earth did that missing mass go?
Well, the answer comes from arguably the most famous equation in human history, written by Albert Einstein back in 1907, E=mc². Einstein basically proved that mass and energy are just 2 sides of the exact same coin. So that missing weight, it didn't just vanish into thin air. It was converted entirely into pure energy, specifically what we call binding energy. It's literally the energy that holds the nucleus together.
Moving right along to Section 3, nuclear fission and chain reactions. So how do we actually trigger this energy? It happens through this process of elegant violence called nuclear fission. Imagine taking an isotope, uranium-235, and smacking it with a really slow-moving thermal neutron. We're talking incredibly low energy here, under half an electron volt. When that slow neutron hits the unstable U-235 nucleus, it literally splits it apart. That split releases a massive 200 mega-electron volts of energy per atom. And the really crucial part? It spits out even more neutrons, which then go flying off to smash into other uranium atoms, creating a massive, self-sustaining chain reaction.
But we've got to be completely real about the engineering side of this. We aren't converting the whole rock into pure energy, not even close. Out of an entire kilogram of completely fissioned uranium, only about 1 single gram of mass actually becomes pure energy. The remaining 999 grams, they don't just disappear, they're left behind as highly radioactive waste. It's a really important nuance to keep in mind when we talk about the unbelievable efficiency of nuclear fuel versus the reality of environmental waste management.
Which leads us perfectly to Section 4, the importance of uranium enrichment. And this brilliantly illustrates our next big hurdle. See, natural uranium doesn't just undergo fission easily, because it contains less than 0.7% of that highly reactive U-235 isotope we need. Most of it is just stable U-238. So depending on what we're trying to build, we have to artificially enrich it. Commercial light water reactors,
they need about 3 to 5% U-235. A compact nuclear submarine requires roughly 20%, and if you're building atomic weapons, you're looking at upwards of 90% enrichment.
The really tricky part is that U-235 and U-238 are chemically identical. You can only separate them by their super tiny physical difference in weight, which means using massive centrifuges or complex gas diffusion. It is phenomenally difficult. Just to give you an idea, to yield 1 single kilogram of 90% highly enriched uranium, you have to process over 150 kilograms of natural uranium. All that leftover, stripped-down material becomes what we call depleted uranium.
All right, Section 5. How does a nuclear reactor work?
So, now that we have our enriched fuel, how do we use it? Well, at a macro level, a nuclear plant is basically just the world's most sophisticated steam engine. It works in 5 main steps. First, that chain reaction we talked about kicks off in the reactor core. Second, a moderator, usually just regular or heavy water, is used to slow the neutrons down so the fission can actually keep happening. Third, all that intense heat is transferred to a heat exchanger, which boils water in a totally separate circuit to create high-pressure steam. Fourth, that powerful steam spins a massive turbine. And finally, step 5, the turbine drives a generator, churning out the electricity we use every single day.
Of course, you can't just have a nuclear fire sitting out in the open. Safety is absolutely paramount here. The primary water rushing through the core gets insanely hot, around 450 degrees Celsius, but it doesn't boil because it's kept under a crushing pressure of 150 atmospheres. And to keep the outside world completely safe from radiation, the containment structure is heavily layered. We're talking an inner shield of fire brick, layers of water and solid steel, all encased in a massive 1.5 to 2 meters of solid concrete.
So let's bring this explainer full circle. If you want to operate a massive 1,000 megawatt power plant, a traditional coal plant is going to require burning around 3 million tons of coal over the course of a year. But to get that exact same steady power from a nuclear reactor, you literally only need about 2 kilograms of enriched U-235 fuel per day. The sheer energy density of this stuff is just totally unmatched by any other terrestrial fuel source.
And there's a vital environmental angle here too. Because we are using the heat of the atom instead of combustion, generating just 1 gigawatt-hour of nuclear electricity prevents the emission of 1,041 tons of carbon dioxide when you compare it to a traditional coal-fired plant. It gives us massive, reliable baseload power with absolute zero carbon emissions.
Which leaves us with a really compelling question for our future. We've seen the mind-blowing physics, the incredibly complex engineering, and the undeniable environmental benefits. We literally know how to turn stones into light. But given the amazing efficiency of this tech, alongside the very real complexities of enrichment and waste management, how is humanity going to balance the awesome power of the atom with our soaring, carbon-free energy demands of tomorrow? Thank you so much for joining me for this explainer. I hope it sparked your curiosity, and I really encourage you to keep exploring.